we just knocked these together out of not much. And it's designed to evaluate light curves, we'll call it. So each one of these attenuates the light intensity just a little bit, but it doesn't change the spectrum, and that's important. So if you start dimming the light or doing something with the ballast, then you change the color temperature of the lamp and its spectrum changes, so that could influence your experiment differentially. So we use these, and then here's a water bath that takes some of the long wave out. And so this is a very standard technique for doing what's called a light curve. So we turn this 1,000 watt lamp on, and it just blasts. I'm serious, it really is bright. And so we have to take a little bit of the heat, and then we just start attenuating it, and you can measure photosynthesis on an ongoing basis. You can measure the evolution of oxygen, you can measure the consumption of carbon dioxide very precisely, in parts per million kind of resolution. Do you have a question?
Is that an actual spectrum light bulb?
No, this is a high pressure sodium lamp, conventional greenhouse lamp. Nothing special at all. We have quite a range of different lighting systems. Metal halide, high pressure sodium, sulfur powered microwave or sulfur coated microwave lamps that do have a very special spectrum. In fact, their daylight spectrum is cleaner than the sun. It doesn't have a whole lot of leakage off into the blues and reds, the long wave and the short wave stuff. So having said that, and it's also extremely efficient in terms of you plug it in and get watts of energy from there, converted to micromoles per square meter per second of photosynthetically active radiation. The microwave lamps are the single most efficient, in that case, system on the planet today. The problem with them is there's moving parts in this light. The bulb spins around inside a little radio frequency cage, and then you have these two collimated beams of microwaves that are blasted at this little ping pong sized ball, glass quartz ball on the end of a glass rod. There's no wires or anything, and there's a sulfur compound inside it, and you mess with the chemistry of the sulfur compound, and you can shift the spectrum of the light that comes out. It was originally designed, I think, in Japan, and it was designed to generate really high intensity ultraviolet, and they used it in the printed circuit board industry to photo etch printed circuit boards for the automotive industry, actually. So they had these, and I bought one of these ultraviolet lamps, 3,500 watt ultraviolet lamp, and you turned it on, I swear it recoiled. It was an extreme, and we called it the death ray, because you literally couldn't be anywhere near it when you turned it on. It had to be in a room all by itself, because it was an extremely intense ultraviolet source. And we used it many years ago to kill zebra mussels. There was a collaboration with a group in St. Catharines, and the St. Catharines Reservoir was totally infested with zebra mussels. I mean, you put a chain down there, and one single chain would come out and be that thick with zebra mussels. Absolutely just like a Bible story or something like that. So we just set up this little trailer, 20-foot Atco construction trailer, split in half, so 2 10 by 10 rooms, and one room had the death ray in it and a tank, and we circulated through that tank water continuously from the reservoir, and so we know what its infection rate was, and the Belliger larvae and all through into zoology and that sort of thing. I had a little drift over to the dark side there briefly, and these larvae, we would put them into a 30 centimeters, so about a foot deep, and 30 centimeters. So that cube, and the water was going through there 100 liters a minute, and this death ray killed all organic life in it. There was 100% latent mortality of anything that wiggled in there, including larvae, zebra mussel larvae that were starting to get little shells on them. It zapped them too, swimming through at 100 liters a minute. So very effective way to clean the water, I'll tell you. And then at the end of the summer, this went on, and we did all kinds of samples and all this stuff. And at the end of the summer, I went in there to collect some of the hardware, and I slammed the door a little bit too hard, and the whole trailer just fell apart. It just collapsed in on itself, the whole, where the ultraviolet light was. It because all the suspended ceiling bits, the plastic ribs and the gaskets and everything on the windows and everything, well, they didn't like ultraviolet light, and they just turned to dust after a couple of months of the radiation. So that's the way that story ended. But, we wrote the papers, sent some technical information to the provincial government, but nothing ever came of it, which is the vast majority of stuff we do. However, I must have generated at least one question by now. All too clear?
Wondering how you provide your research for drilling on the moon versus on Mars, kind of these things. Like what do you see as your priority versus what your investors trying to
The moon
make
and
your
Mars,
priority?
essentially no different, technically, at this point. We use the moon as a test base for Mars, just like we're using Devon Island as a test base for the moon.
Okay.
And we're using here as a test base for Devon Island. So it's a very sequential and more or less sensible escalation of technology readiness and challenge, remote challenges, harsh environment challenges. As far as space, like microgravity applications,
Yeah.
none.
Okay.
Absolutely none. I would say in this century, and possibly beyond, there should be, and probably will be, no requirement for a significant biological system in a low Earth orbit application or a transit application, like a Mars transit. For 6 months, I can carry enough crap. I can even have babies. But it's when you're talking 5, 10 years, long-term habitation, long-term rotations of crews where you're building up crew on Mars, for example, to do the exploration, or you found mountains of diamonds just below the surface or something. God knows what we're going to find. It's going to be, we'll almost certainly find life on Mars in some form. I'm almost convinced that, not very far in the big bucket of water we found in August last year, there's going to be some microbial vestiges of microbial life. We may even find that that's where we started. Who knows? But anyway, that kind of prospect, long-term habitation, is where you'll start to consider building up habitation, building up a biological life support. And slowly but surely, biological life support will catch up with physical chemical systems and resupply requirements and replace them, because it must. But on a station, a few hundred kilometers away, you just send a tourist break to people up there with some oranges from Florida, and everybody's happy. Or on a 6-month transit, you just carry it on. We've got lots of experience. My good buddy Bob First just went up. He's the one who's going to get the seeds from Julie when she gets there. The tomato seeds that we then send to 11,000 rations across Canada. That's our outreach story. So for that, you don't need biological life support. You can't afford the mass and energy, especially the energy. And imagine if you tried to support even 1%, 2% of the food requirement for a crew of 6. You need square meters, you need chambers, you need all kinds of lighting systems and horticultural management, crew time. The equivalent system mass, as it's called, would be inordinately expensive and impractical. It won't happen. But it must happen, especially on Mars. And it took me 4 years, as I said, to grow a lettuce remotely, robotically, automatically on Devon Island. Now, Devon Island arguably is harder to get to than the moon, but notwithstanding that, it still took 4 years for us to master the technology, to push a button here in Guelph or in St. Hubert, and then have salad when you arrive there with the crew in July. And that was an eye-opener. We figured, we can handle that, we're with the big stuff. That's 12 greenhouse folks, we knew all this stuff. It was casual. Not. So when you consider trying to do it on the moon, where the early plant growth experiments, investigating lunar radiation environment effects on plants,